Okay, lesson 3, interpreting and using function notation. Let's, as usual, get our learning targets in. I can describe the connections between a statement in function notation and the graph, right? So describing the connections, we can use function notation to efficiently represent a relationship between two quantities, right? So using the notation to connect two quantities, and then using the statements in function notation to sketch a graph. All right, here we go. Make sure that the learning targets are in your notes. So we're talking about observing a drone. Observing a drone. So here's a graph, right? Right here is the graph that represents the function f, which gives the height of the drone in meters, right? So height is in meters. T seconds after it leaves the ground. So here's our time in seconds. So f of 0, right? Remember, we have this idea of f of x, right? Equals some y value. So f of 0, the height is 0. At 4 seconds after, the height is 1, 2, 3, 4 lines above the origin there. So I don't know, say 4 meters. I'm not really sure what the units are on the left side. There's no units, but all I could tell you is that the value of f of 4 is greater than the value of f of 0, because I'm comparing the y value at 0 compared to the y value at time of 4. Comparing f of 2 to f of 5, I'm going to go from 2 and then over, and then f of 5 and over. It looks like they are the same or equal. So neither is greater. F of 3, again, all the way to that top part, versus f of 7, back to 0, then f of 3 is greater. And for the last one, f of t, so any given time from 0 all the way to 7, versus that time given plus 1 second. So 0 would be t, and 0 plus 1 would be here. So f of t plus 1 would be greater. But what if f of t was f of 2? F of t plus 1 would be 3, and they would be the same. What about f of 5? If t were 5, f of t plus 1 would be 6, then the f of t would be greater. So there are times when f of t plus 1 would be greater, there are times when f of t would be greater, and there are times when they would be equal. So it depends on what the value of t is. That's sort of an unanswerable question. The function p gives the number of people in millions, right? So number of people in millions, so that's our unit count, who own a smartphone t years after 2000. So it sounds like years is our independent variable, right? That acts like our x. And number of people is our dependent variable. That acts like our y value. What does each equation tell us about smartphone ownership? So again, this is always our independent variable, or our x value, and this is the dependent, or our y value. So it looks to be that 17 years after 2000, or in 2017, the number of people that own smartphones is 2,320 million. All right, so because the number was the number of people in millions, so we have to add some zeros to this. 6 zeros to be specific, because if you had a 1 right here, this would be 1,000. And if you had a 1 right here, that would be 1 million. If you had a 1 here, that would be 1 billion. So if you look at this, this is 2.3 billion, or 2,320,000,000. Wow, that's a lot of smartphones. But back to the interpretation. In 2017, right? In 2017, where did I get that from? 17 years after 2000. So in 2017, about 2,320 million or 2.32 billion people owned a smartphone. That's the output. How about P of negative 10? Well, if negative 10 is the number of years after 2000, if it's negative, that must mean before 2000. So what's 10 years before 2000? I guess that would be 1990, right? How many people owned a smartphone in 1990? None. And why not? Because there were no smartphones in 1990. That'd be when I was in high school. Wow. We were just forced to pay attention in school. Now what they want me to do is go in the reverse direction, right? Use function notation to represent each statement. So in 2010, that's 10 years after 2000. So I guess that's going to be P of 10. The number of people who own a smartphone was, let's see, now we have the millions is there. So that's 296.6 million. So that equals 296.6. In 2015, so how many years is that after 2000? That's 15 years. So that's P of 15 is going to be equal to, and now we got this 1.86 billion. So let's write that out. 1.86 billion would be thousands, millions, billions. So if we want to write this in millions, we're going to remove the 6 zeros. That's 1,860. That's what that looks like. And that's the interpretation. So again, just to recap, from statement notation here into a statement, and from statement into notation, backwards and forwards. No problem. Okay, so it says May is curious about the T, and P of T equals 1,000. Now keep in mind that this is 1,000 million, so 1,000, but with 6 zeros on the end. So to correctly interpret this, that's 1 billion. So what would we tell May about the situation? I'd say T represents the year when 1 billion people owned a smartphone, right? Adding the value of T to 2000 would give you that year. So if T was 7, then we'd say in 2007, that's the point when 1 billion owned a smartphone, so on and so forth. Now for part B, is 4 a possible value of T here? So in 2004, could there have been 1 billion owners of a phone? I think this is easier answered if we draw the sketch down here first. So let's use what we have so far. Sort of going along the line of timeline, we know that 10 years before 2000, 0 people owned a cell phone, right? So that's that. And again, keeping in mind this is population in millions, we were given that in 10 years since 2000, or at the T equals 10, the number was about 296, which puts us right around there, 296.6. We said that in year 15, or 2015, which is 15 and a number of years right here, that the value was 1,860. So that's going to be right around there. And then 17, right? 2017, 2320. And so we have these dots to sort of connect the lines. So I'm just going to kind of leave it at 0, and then it sort of goes, and then smartphones take off, and thus controlling the brains of many weak-minded people. But anyway, this rise of smartphone usage, and I find it interesting. I think the owners of the phones tend to be the people that are smart, right? You should be a smart owner of a smartphone. But again, is that the case? I don't know. But anyway, look at, is 4 a possible value of T? Is it possible that 4 is when we hit 1 billion? I don't think so, because you would need 1,000 for our graph would indicate that that's 1 billion. So 1,000 doesn't happen until right around here. So I would say No, not possible. The value has to be much smaller at a t of 4. I don't know the value. I'm just arguing that it can't be a billion. And here's just a book example or cleaner example of the graph and then the book explanation of part B. Make sure you get this into your notes. And if you have questions about it, ask during class time. Moving along, boiling water. The function W gives the temperature in degrees Fahrenheit of a pot of water on a stove t minutes after the stove is turned on. So again, got to think about this. Minutes is going to be our independent time, and that's number of minutes since the stove is turned on. So from 0 minutes on down to, well, I don't know, looks like the biggest number here is 30 in terms of minutes. And then over here, we're going to have temp, right, in degrees Fahrenheit, okay? And that's that. And just for the record, water boils at 212 degrees Fahrenheit. That's boiling. So take turns with your partner, well, I'm kind of your partner at this point, to explain the meaning of each statement in the situation. When it's your partner's turn, listen carefully. If you disagree, discuss it. So it's going to be hard to discuss it, so we're just going to have to focus on the listen carefully. So W of 0 is 72. That means that at time of 0 minutes, the temperature of the water is 72 degrees. Or in essence, I guess the water temperature that we put into the pot to begin with was 72 degrees, which is probably ambient temperature of the faucet water or ambient temperature of the room if the water had been sitting around. Next, we have W of 5 minutes is greater than W of 2 minutes. Well, that makes sense, right? If the time that it's been sitting on the stove, right, I imagine getting heated after the stove is turned on, then the longer it sits on the stove, the higher the temperature, right? So the temperature after 5 minutes is bigger than or greater than the temperature after 2 minutes. Makes sense to me. All right. The temperature after 10 minutes is 212. Oh, it's boiling, right? So I guess it took 10 minutes to boil. Now notice the difference here. There's no W on this side. Again, when I say W of 5, that means the water temperature after 5 minutes, water temperature after 0 minutes, water temperature after 2 minutes is 72 degrees versus is greater than the other temperature at said time. So this is water temperature after 10 minutes is 212 degrees Fahrenheit. Moving right along, the water temperature after 12 minutes is equal to the water temperature after 10 minutes, right? So again, once that water reaches a boiling point, 212 degrees, I guess it's just going to stay around 212 degrees. It's boiling and now it's just beginning to evaporate. So the water temperature after 12 minutes is the same as the water temperature after 10 minutes. We must have kept, right? We have the stove at a certain temperature and we've raised the water to that temperature. Now, as this is happening, I just want to keep an eye on the graph. What's happening? As the time goes on, the temperature went up, and now it's sort of staying constant. Let's look further in the situation. After 15 minutes, right, the water temperature after 15 minutes is greater than the water temperature after 30 minutes, which means after 15 minutes, the water temperature starts to go down, right? Somewhere between 15 minutes and 30 minutes, the water temperature has decreased, and when we look at the temperature of after 0 minutes is less than the temperature after 30 minutes. So the water is warmer after 30 minutes than it was to begin with. So it sounds like it's done something like that and sort of like tapered off at that moment if this were the 30-minute mark. So here's these last two right here and kind of alluding to the graph which is coming up. So if all the statements in the previous question represent the situation, sketch a possible graph, right? We don't actually know the 100% what's going on, but it said, and I had a little bit off in my previous sketch. I said at 0, it was down at 0. At 0, it was around 72 degrees. And then I believe after 10 minutes, it was at 212 degrees. And I kind of just drew it behind the scenes there. So at 10 minutes, around 212. And I know at 12 minutes, so it's not perfectly in between here, but right here, 12 minutes, we had the same temperature. And then it said at 15 minutes, it was warmer than it was at 30. And at 30 minutes, it was warmer than it was at 0. So the 30-minute mark is higher than the 0. The 15-minute is higher than the 30 minutes. And 15 is not too far from the 12. So let's just assume we boil it for, 3 minutes or so. It very well could have been something like this, right? Where it went up and then it boiled for longer than that and then it came down. I don't really know when it stopped boiling. All I know is that it did eventually and then it came back down. And it most likely came down in a linear fashion. Here's the book's version of it, or the author's answer key version of it. Again, starts at a temperature of around 70 change, boils at 10. They chose to drop it down from 15 down to 30, and notice at 30, it is definitely at a higher temperature than it was when we started. Of course, the water wasn't 0 degrees when we started, which is a little bit of a faux pas for my initial sketch there. That would have been frozen water, and I don't think we poured frozen water into the bucket or into the pot. So in summary, what does a statement like P of 3 equal 12 mean? Well, on its own, P of 3 equals 12 only tells us that when P takes 3 as the input, right? 3 is the input, 12 is its output. If we know what quantities the input and the output represent, however, right, we can learn much more about the situation, right? So if P gives us the perimeter of a square whose side length is x, then that means that we can interpret P of 3 to mean a square whose side length is 3 has a perimeter of 12, right? So now P of 3 equals 12 is much more meaningful. We can also interpret things like P of x equals 32 to mean a square with a side length of x gives a perimeter of 8 inches. And we know that there's 4 sides and they're all equal. So if you divide 32 by 4, you can figure out that 8, right? You can argue, right? Or reason. That's the best part about mathematics, our ability to build reasoning. 8 inches is the side length. So then we can deduce that P of 8 equals 32. If function P gives the number of blog subscribers in thousands and X months after a blogger starts to publish online, then P of 3 means 3 months after they have 12,000 subscribers, right? 3 months after the blogger starts publishing, 12,000 subscribers. So it's important, right? It's critical. It's imperative, monumental, that we pay attention to the units of measurement when analyzing. If we miss that P of X is measured in thousands, we might say that P of X equals 36 to mean that there are 36 bloggers after X months, which actually means there's 36,000. That's a huge misunderstanding. A graph of a function can likewise help us interpret statements in a function, right? So if function f over here, so this whole thing is the function f, gives depth in inches, right? Depth of water in inches of water in a tub. And T is minutes since the tub is being drained. Again, the water is going to go down. And it looks like the water level stops at 2 and change inches. So maybe there's a clog or something. The water's not draining, right? Maybe they shut the drain back off. I don't know. Each point on the graph is T and F of T, right? So again, when I look at that T, F of T, I'm thinking X, Y coordinates. So F of T is a fancy way of saying Y, where the first input of the function, right, where the first value is the input and the second value is the output. So F of 2 represents the amount of water after 2 minutes. So I follow the 2 up, I go over, F of 2 is 5. F of 2 of 5 captures that information, right? 2 minutes after the tub was being drained, there was 5 inches of water. F of 0 gives the depth of the water when the draining began, right? So the depth of the water was originally at 6 inches. And F of T equals 3 tells us that after so much time, there was 3 inches of water, I can follow that 3 over and then down. So T must have been 6. Again, using a graph to help us interpret statements and find missing values. So taking this idea of paying close attention to the units, we have at noon, a news organization published a piece of breaking news on its website. The function Q gives the number of visitors in thousands, number of visitors in thousands. And to the website H hours after the news was published. So the input is the number of hours since the news was published. By 2:30, the news article had been viewed by 1.6 million visitors. So which of these represents that scenario? Well, first off, it's going to be by 2:30, which is 2.5 hours since noon. So I think I'm looking for Q of 2:30, Q of 2:30, Q of 2.5, 2.5, 2.5. So I think that I'm looking for 2.5s, right? Now, which one of these outputs is the real version of 1.6 million? So it's representing 1.6 million, but the number itself represents millions. The actual number is in thousands. So again, if you take a number, say 2, and that number is representing in thousands, then 2 technically means 2,000. So I got to put 3 zeros on the end of these first to be able to interpret this correctly. Okay, so back to our contestants. I'm looking for 1.6 million. So I've added the 000 on because they were all represented in thousands. So this is going to be 16,000. No. This is going to be 1.6 million. I think that's the one. And then this one right here is going to be 1.6 billion. So no dice. All right. And that's it for notes. Good job. See you in class.